Well, hello everyone, and welcome to the April installment of the National Weather Association's Webinar Wednesday. My name is Becca Mazer. I am Committee Chair for the Professional Development Committee and will be your host for today's webinar. A few logistics before we get started here. Everyone in attendance will be kept on mute for the entirety of the talk, but you can ask your questions throughout the webinar by either using the question feature on the GoToWebinar GUI, or you can ask your question using the hashtag NWAWebWed on Twitter. I will then read the questions. There will be a section in the middle of Chris's presentation that he will ask for questions, so I will ask those of him sometime in the middle of the presentation and then also at the end of the presentation. You can follow along on Twitter using the same hashtag, NWAWebWed, or follow the NWA account at NWAS. And this webinar is being recorded for later viewing. So I am pleased to introduce our speaker today, Chris Vagasky. He will be talking on the subject of lightning basics and the enveloped Eyewall lightning signature. Chris is the North America Sounding Solutions Manager with Vaisala and has been with the company for 3.5 years. He primarily handles specialized upper air measurement support, but has a particular interest in lightning and lightning education. Take it away, Chris.
Okay, thank you, Becca, and thank you everybody for joining us today. As Becca alluded to, our topic today is lightning basics and the enveloped Eyewall lightning signature. We'll get into that here shortly, but I do want to introduce myself if you are not familiar with me. My name is Chris Vagasky. I have both my bachelor's and master's in meteorology. I attended the University of Oklahoma and Mississippi State University. As she said, I am the Sounding Solutions Manager, which means I get to play with weather balloons a lot, but I do have particular interest in lightning, understanding lightning, applications of lightning, and things like that. And if you are not following me on Twitter, please feel free to do so. I do post a lot of interesting lightning loops and have some good conversations about lightning on my Twitter account. So where are we headed? This is going to be kind of a 50-50 lightning basics and lightning applications today. So we'll get started with some definitions, a brief, how does lightning develop? Why should we care about lightning? Ways to detect lightning, and then we'll get into the applications after that. So as we get started, it's definitely important to have some definitions of terms you may hear when you are discussing lightning. The first one would be cloud lightning, and of course that's lightning that occurs within a cloud, between multiple clouds, or between the cloud and the air. That is the majority of lightning in a lightning storm. On the other hand, the lightning that impacts most people would be the cloud to ground lightning, occasionally ground to cloud. And that is any lightning event that makes contact with the ground. And that accounts for 10 to 50% of the lightning in a lightning storm. Now, traditionally, when people talk about lightning, they say, oh, yep, there's a strike of lightning over there. Well, that is kind of an incorrect usage of the term lightning strike, because lightning is really classified as either a lightning flash, which is the total lightning discharge, or a lightning stroke, and those are the individual components of a lightning discharge, of a lightning flash. And lightning strokes are why lightning appears to flicker. An individual lightning flash, and we'll see this on the next slide, may have multiple lightning strokes and therefore multiple ground strike points. And this is why calling a lightning flash a lightning strike is an inaccurate or an incorrect use of the term strike. This image here is kind of complex and complicated if you aren't really familiar with looking at lightning mapping. So I'll kind of describe what we're looking at here. This top image looks at the altitude above the ground, and then this is a time plot along the x-axis. So time moves forward as you go to the right. Each of these little dots is a part of the lightning flash. And you can see how the lightning starts in the cloud between 8 to 10 kilometers and then comes down to make the ground contact. In the bottom right, or sorry, the bottom left, we see how this is a 2-stroke lightning flash. First, the blues and greens into the yellows make the first lightning stroke, and then about a quarter second later, you get the second lightning stroke following the same channel. So this shows how one lightning flash can be made up of multiple strokes and multiple ground strike points. I wanted to talk briefly about how lightning develops if you're not intimately familiar with the lightning process. In a cloud, you'll often have mixed phase water, so your supercooled water droplets, graupel, hail. And as the updrafts and downdrafts interact with all of this mixed phase water, graupel, supercooled water is lighter than hail, lighter than an ice crystal. So you start getting interactions between the particles as they rise and fall in that cloud. And as they collide, ions or electrons are exchanged. You get positive and negative regions within the cloud. And when the charge separation is great enough, you get that discharge of electricity, which we know as lightning. Now, why should we care about lightning as meteorologists? Well, it occurs in every thunderstorm. You don't get thunder without lightning. So a thunderstorm is a lightning storm. 30% of all power line failures are lightning related, so it has major impacts on the population, on power transmission, impacts to recreation, entertainment, property. And a big one, there are up to 24,000 lightning deaths worldwide every year. Ron Hawley did a study of this 2 years ago for the International Lightning Detection Conference, where he analyzed data that comes from the United States, Mexico, other countries throughout the world, and estimates that up to 24,000 lightning deaths occur worldwide every year. We're doing much better here in the United States. As we can see in this image of lightning deaths from 1940 to 2017, this data is all available from the National Weather Service. Back in the 1940s, lightning fatalities were a major issue. We've had almost 450 lightning fatalities during the Second World War a year. But due to changes in the United States economy, in where people live, and with lightning safety becoming a big thing with the National Weather Service and meteorologists across the United States, lightning fatalities have dropped off precipitously. And last year was a record low for lightning fatalities when we had less than 20 in the United States. I've also shown on this chart the 30, 10, and 5-year running averages of lightning fatalities. And I want to point out that, as meteorologists, we traditionally think of climatology in terms of a 30-year average. But when your statistics or the data that you're looking at are not a steady state, as in lightning, where it's kind of been improving exponentially. Using a 30-year average does not really tell the true story of lightning safety. If you are looking at 2017 and your previous 30 years have included lightning fatality years of the late 80s, where nearly 100 people a year died due to lightning, you are not accounting for the fact that we have made rapid improvements in lightning safety, and a 5-year or a 10-year running average is more appropriate for telling the story of lightning safety. A 30-year running average is about 50 lightning deaths per year. A 5 or a 10-year running average is closer to what our current average is of about 30 deaths per year. This is all kind of a good lead-in, talking about how does lightning develop and why should we care about lightning, into, okay, well, how do we know what or where the lightning is? And that is how lightning is detected. Traditionally, lightning has been detected through ground-based sensors operating on very high, low, and very low frequency spectrum, measuring the electromagnetic fields of the lightning. Of course, we've also now added satellite-based sensors that are working on as an optical sensor to provide very close range and long range lightning detection capabilities. The high frequency sensors detect the in-cloud lightning and some of the cloud-to-ground lightning at a very close range. Your low frequency and very low frequency sensors are for your continental scale and your global scale lightning networks. Some definitions when it comes to lightning detection. The baseline, that is the distance between your lightning sensors. A uniform baseline gives you uniform coverage. When you have a varied baseline, some areas may have better coverage than others, and that is especially important when you're thinking about the type of sensor that you're using, if it's a low frequency or a high frequency sensor. The detection efficiency, that's what percentage of the lightning is detected. Your location accuracy, so how close to the actual ground contact point or the lightning pulse in the cloud did the system say that the lightning was. And traditionally, there have been two types of lightning detection techniques. One of them is magnetic direction finding. The other is time of arrival. We'll get into those shortly. But before we do, I wanted to discuss some of the existing lightning detection technologies. This is adapted from a chart that Ken Cummins shared at the International Lightning Detection Conference this year, which compares the various types of lightning detection that are currently in use in the United States. The lightning mapping, which gives you images similar to the first image I showed of the 2-stroke lightning flash. Your partial total lightning detection in the yellow, and those are your National Lightning Detection Network, your Earth Networks Total Lightning Network, the US Precision Lightning Network. And then very low frequency techniques which provide global lightning detection, like the Global Lightning Dataset 360 and the Worldwide Lightning Location Network. We can also add in GLM. Now, it's important to see that there is nothing up in this upper left corner, which is where we've labeled the best possible lightning detection system, which would give global coverage at a very fine spatial resolution. Currently, we're at our best able to see at a small spatial resolution up to about 100,000 kilometers or 500,000 kilometers. Longer ranges, we're able to detect globally within a kilometer or two. If we can get out to this best possible, then we're making, drastic improvements to the current lightning detection technologies. But what we have right now is currently just phenomenal. I want to touch now on how lightning detection techniques work. The first is we'll look at the time of arrival technique. And in the time of arrival technique, you have the lightning contacting the ground. So it contacts at this red dot. The green, purple, and blue dotted lines tell when the lightning reaches a particular point between these individual sensors. So between sensors 2 and 3, 1 and 3 in the blue line, and 1 and 2 in the purple line. Each of these dotted lines intersects based on the time that it takes the low frequency signal to propagate away from the lightning. And where they intersect, that is where the system detects that the lightning occurred. You can do this with a minimum of 3 sensors. However, in some cases, if you're only using 3 sensors, you can get a secondary intersection of these lines of time of arrival, and you can get a falsely located lightning stroke. So to have a truly unique solution with a time of arrival system, you need a minimum of 4 sensors. Now, on the other hand, with magnetic direction finding, you can get by with just 3 sensors. As the lightning magnetic field propagates towards each sensor, the antenna then triangulates and points in the direction that the magnetic field came from. Each sensor points in a particular direction, and you can use algorithms to minimize the error of the angles that each sensor has provided to give you a location. Now, the optimal lightning location method combines both time of arrival and magnetic direction finding. By including magnetic direction finding, you're able to use only 3 sensors, which increases your detection efficiency. A time of arrival system is generally better at location accuracy because you minimize impacts of local magnetic fields, the terrain, and things like that. So by combining the two, you get the best of the direction efficiency and the best of the location accuracy. Now, this is a lot of information that I've kind of thrown at you in a short period of time. So I want to pause and take any questions that may be had on either lightning detection or on just some of the basics of lightning that we talked about.
Again, please use the hashtag NWAWebWed or ask your question real quickly in the GoToWebinar GUI. Right now, we don't have anybody asking questions, but we can give it a minute or so.
Yeah, I'll give it a minute. There was a lot of information to absorb. So we'll let it percolate, and if anybody has questions, I'm absolutely willing to answer them.
In the meantime, do you want to share a story of watching lightning or anything like that? Photographing lightning?
You know, photographing lightning is a very hard thing to do. You have to anticipate it. Otherwise, if you have, very high-speed cameras, you get amazing lightning photography. And that was one of every 2 years, the International Lightning Detection Conference is hosted at different locations around the United States. And this year they showed the top 10 high-speed lightning videos. So these were all videos that were taken by cameras that were shooting at 1,000, 10,000, 100,000 frames per second. So you saw each individual step of the lightning as it came out of the cloud to the ground. So if you want to waste a lot of time, look up high-speed lightning videos, because you can definitely have a lot of fun watching those.
Yeah, I've seen a couple and they're pretty neat. Well, I see no questions yet, so you can go ahead and continue.
Okay, we're going to go now from the kind of the basics of lightning and lightning detection into probably what I consider the most important part of lightning, and is what do these dots on the map mean? So, the Weather Service has lightning data feeds. Our broadcasters, they get lightning data feeds into their radar systems. And you're looking at it and you say, okay, yeah, there's lightning on the map here, but knowing and understanding what those dots on the map mean can really help you as you're diagnosing a weather event. Now, I want to start with a caveat, and it's important to know what data your system is showing. Do you have total lightning, or do you have only cloud to ground lightning data? This first map here shows a line of storms that is moving from west to east. And each plus sign or square on the map is a detected cloud to ground lightning stroke. So, we have some lightning that's on the leading edge of the storm, where you would traditionally expect to see the lightning. But then on the western edge in the stratiform region, there's a positive cloud to ground lightning stroke. Now, if we show you total lightning, so that's your cloud and your cloud to ground lightning, you can see there are a lot more dots on the map. And each of these different colors corresponds to a time that the lightning was detected previous from right now. So the black is within 15 minutes, the red is between 15 and 30 minutes, and so on. So in the purple circle, that positive cloud to ground lightning stroke had 10 to 15 minutes, up to 20 minutes of kind of advanced warning. Because anywhere that there is cloud lightning, there is a chance for cloud to ground lightning. And this is important to think about when you're dealing with a squall line or anything where there is a stratiform precipitation area. If you have cloud lightning in that stratiform region, there is a chance that cloud lightning could then end up as cloud to ground lightning. And when you're not in the true core of the thunderstorm, you're probably thinking that you're okay in terms of lightning, but that's not always the case. I'm going to jump into winter weather. We're eventually going to get out of this winter pattern that we've been in, even though the upper Midwest this week will be getting some more snow. But this loop shows a blizzard from a couple of years ago, and you can see your banded precipitation. And When there's banded precipitation, you tend to look at those areas for heavier snow totals. Well, there is also one band which has cloud-to-ground lightning detected in it. Now, Jim Cantori is jumping up and down. All right, we've got some thunder snow. Well, thunder snow is another place where enhanced precipitation totals occur, even more so than in just traditional banded precipitation. So if you are monitoring radar trends and you see banded precipitation, okay, you know we're going to start to see some enhanced snowfall. And then when you add lightning into those bands, those are your areas where there's even heavier precipitation. I'm going to show next a loop of more thunder snow, but in this case, the thunder snow didn't increase the snow totals. This is in the thumb of Michigan, as a lake effect snow band came off of Lake Huron and crossed into Huron County, Michigan. Now, this was New Year's Eve 2017. This snow band crossed into Huron County, Michigan. It passed over multiple wind farms. And this lightning was actually initiated by the wind farms. Wind turbines and tall towers, such as TV transmission towers, radio transmission towers, and things along those of that nature, can help initiate lightning in winter weather events where there's a very low cloud layer and a charge in the cloud as the snow and other ice crystals collide in the cloud. And this tower initiated or wind turbine initiated lightning can cause potential issues with power and transmission and damage to wind turbine blades, the mechanics of the wind turbines. And of course, it's a potential safety hazard to people who may be outside and not expecting any lightning, but if they're near a tall tower or a wind farm, there may be cloud-to-ground lightning that occurs when they weren't expecting it in the middle of winter. So now we've kind of briefly touched on winter weather and how to look at lightning in a winter weather case. Well, now we're getting into the true convective season. So we'll look at using lightning in the convective season. So this is essentially a real-time analysis of a storm system that was moving into the southwest sides of Houston a few weeks ago. And the lightning data is updating every minute. And these are your traditional 5, 6, 7 minute radar updates. Again, the color coding on all of the lightning corresponds to the time that the lightning occurred. This is between 0 and 25 minutes previously, from black to purple. And you can get a lot of information out of this watching the lightning update in 1 minute increments versus the radar sweeps every 5 to 7 minutes. You get an indication of the trajectory and the path of the storms as they move in much faster time than the radar image. You can also see where the more intense cores are, where the higher lightning densities are. And then even as a new storm develops behind the leading edge, you get an indication of that with seeing new lightning appear behind the initial line of storms before necessarily the radar data shows up showing the high reflectivity. This it really just goes to show how much you can get separation between the radar reflectivity and your actual lightning data based on looking at 1 minute lightning data versus your radar sweeps as they come in. And on the back end of the MCS there, you do see this new developing storm where the lightning has developed in advance of the radar reflectivity really showing what you would consider a traditional convective cell. So using lightning in a real-time analysis can give you a heads up on how the storm system is evolving. And this really comes in handy, especially with splitting thunderstorms. This was March 25th. There was some radar issues with the data transmitting that day. But as you look at the radar, or I'm sorry, at the lightning data, you can see the cell. This was a supercell that split near the Red River in Texas and Oklahoma on that day. And you can watch the lightning actually split off into two separate cells before the storm actually, before you actually see the storm split on radar, if there was real-time radar coverage that day. And this can give you, of course, a heads up to a potential left-moving supercell with large hail. If you see the lightning split, then you have a heads up that you may have a splitting storm situation. And again, you see this when you do add the radar in. You see the one cell then split into a right mover and a left mover, but the lightning splits off in advance of seeing the storm split on radar. So using lightning in situations where you may have splitting cells can give you a heads up on potential left movers and right movers. In the case of tornadoes, this storm, which had one cloud to ground lightning stroke, did produce a long-lasting funnel near Calgary in Canada. But just a couple of days later, this storm had a long-lasting tornado over Manitoba and drastically different amounts of lightning. Lightning is not a great predictor of tornadoes. There is a lot of work being done on the lightning jump algorithm and things like that for anticipating severe weather based on the amount of lightning in a storm. But it should be noted that at least 2% of tornadoes do occur without cloud to ground lightning. And that was a study that the SPC presented in 2015. Geyer and Dean looked at tornadoes in the United States and found that at least 2% occurred without cloud to ground lightning. So don't let a lack of lightning lead you to believe that a storm may not necessarily produce a tornado, because it is possible. So now I would like to transition from small spinny things to large spinny things. And we'll talk about the enveloped Eyewall lightning signature. This was actually some work that I published in the JOM last year based on my master's research. And it looks at a particular signature of lightning that completely surrounds the eyewall of a tropical cyclone. So I invite you to read the paper that was published in JOM, but we'll talk briefly about the Eyewall lightning signature now for the rest of the webinar. So why do we care about tropical cyclone lightning? Well, it used to be that the only way you knew about lightning in a tropical cyclone was you were flying a plane through it, or it made landfall and you saw lightning. Well, now with VLF lightning location systems and the satellite-based lightning sensors, we're seeing lightning in tropical cyclones a lot more. And research is being done to try and understand, well, what does it mean? And there are some thoughts on what it means, and it could mean the beginning of an intensification period, the end of an intensification period, going into an eyewall replacement cycle. The storm's about to make landfall. It's about to intensify, it's about to weaken. There's been a lot of uncertainty in exactly what the lightning means, when the lightning occurs, where it occurs in a tropical cyclone. So that's really what we're trying to understand, is how does convection and lightning in a storm impact that storm? So what I'm going to talk to you about today is Hurricane Irma, in particular Hurricane Irma when it was at its peak intensity of around 155 knots. And we will start by showing you a loop of detected lightning in Hurricane Irma on September 6th and 7th. And this circle that is moving north of Puerto Rico, that is the enveloped eyewall lightning signature. It is the signature of detected lightning that completely envelops the eyewall of the tropical cyclone. And we can see as Irma moves to the northwest how the lightning kind of changes its location and the quantities of it. And you see this happen in a lot of storms. Lots of different locations for the lightning, but what I'm going to particularly focus on is this circle of lightning within the eyewall, which we've termed the EEL signature, a ring of lightning that envelops the eyewall of a tropical cyclone and persists for a minimum of 6 hours. And that 6-hour time constraint was used to focus only on the storms that had a long-lasting eyewall lightning outbreak, not the occasional burst of lightning here and a burst of lightning there. And when you add radar to it, you can start to get some ideas about the structure of the storm. And the blue diamonds are the detected lightning strokes in Irma's eyewall. And you can see that while there's a lot of lightning in the eyewall, there is very little lightning in the outer rain bands of Irma. And this is seen a lot in storms that exhibit the EEL signature. You get a lot of lightning in the eyewall and then very little lightning elsewhere. Towards the end of the loop, and we'll let this loop play through again, you'll see that when Irma undergoes the eyewall replacement cycle, lightning essentially shuts off in the eyewall. So there's been a disruption to whatever mechanism is causing the eyewall lightning, and then the lightning then transfers into the outer rain bands. And we'll see this as you see the secondary eyewall begin to form around Irma, new lightning in the secondary eyewall, and the lightning tapers off in the original eyewall. So in Irma, the EEL signature was evident during the peak intensity for about 24 to 30 hours when Irma was at Category 5 intensity around 155 knots. And the ERC essentially shut off the eyewall lightning. So there is a mechanism that is causing this lightning in the eyewall that when it gets disrupted is hard to then start up again after the ERC. And this is very similar to other tropical cyclones that have shown the EEL signature. And in the paper, I've shown that it's primarily associated with high-end tropical cyclones that are 130 knots or stronger. There's a big so what? Okay, you've got lightning in the eyewall, that's cool. But what does it mean? Well, in the 32 storms that I found with the enveloped eyewall lightning signature, it seems that it may have been associated with intensification. The wind speed at the beginning of the EEL signature, 45 to 60 knots. But at the end of the EEL signature, I'm sorry, these are meters per second, so 45 to 60 meters per second. At the end of the EEL signature, between 60 and 70 meters per second. So there's been an increase in the overall wind speed of the storm. And during the signature, wind speeds peak between 65 and 80 meters per second. So these are very strong storms that have the enveloped eyewall lightning. Now, comparing the enveloped eyewall lightning storms to the non-enveloped eyewall lightning storms, the 25th percentile intensity for EEL storms is about the 75th percentile intensity for non-EEL storms. So these are stronger storms than storms that don't have the eyewall lightning. Now, I looked at 4 years of storms globally, looking at it, all storms that reached a minimum intensity of 115 knots. And they tend to be out in the Pacific. Well, that's where most of our tropical cyclones are globally. But every basin does show them. And last year, both hurricanes Irma and Maria showed the eyewall lightning signature, and these were very strong Category 5 hurricanes. So this is something that can be used by tropical forecasters, not just in the United States, but globally. And if you are going to the AMS Tropical Conference next week, I will be presenting some more work on the lightning signature, comparing Irma, Jose, and Maria. These three storms all formed last year within about 4 weeks of each other, and they all passed relatively close to each other. Irma and Maria showed the eyewall lightning signature, but Jose did not. So all three of these storms were 150 mile per hour storms or stronger, yet only 2 of them showed the enveloped eyewall lightning. So maybe there's something in the environmental conditions that can help us to better understand why exactly we're seeing this lightning, so that we can better understand why it's developing and what it means for that storm. And then I'm also looking and doing a possible in-depth dual pole study on Hurricane Irma to better understand what the structure within the eyewall may have been, to better understand that enveloped eyewall lightning. So again, I will open it up for questions on applications of lightning data.
I have one. Well, first of all, do you envision using lightning as a perhaps sort of predictor of tropical storm development in more of the younger stages of the tropical cyclone's life cycle? Especially, once we have more global coverage of lightning with the GLM.
Yeah, there has been work done on cloud clusters in the Eastern Pacific, and the cloud clusters that have more lightning are more likely to become tropical cyclones. So yes, in the earlier stages of development, if you see more lightning in an invest or developing cloud cluster, there appears to be a greater likelihood that it will become a tropical cyclone. Lightning will become and is becoming a good tool for helping to assess the intensity and the structure of tropical cyclones, whether it's a tropical depression, tropical storm, or a major hurricane. So as we get more and more lightning data and look at more and more lightning data in tropical cyclones, we'll start to to get some new ideas on what it may mean for development, intensification, and storm structure. So I'm looking forward to seeing where the future goes with lightning in tropical cyclones.
Awesome. Anybody else have any questions out there? Please type them into the GoToWebinar GUI, either the chat or the questions box, or use the hashtag NWAWebWed on Twitter. All right, looks like we have a few questions for you now. All right, so first and foremost, are lightning detection sensors located on the Earth's surface or only in outer space? If on the surface, where are they located and what do they look like?
Yes, there are both ground-based sensors and space-based sensors. So on GOES 16 and on GOES 17, there are the geostationary lightning mappers. And then on the Earth's surface, there are many ground-based lightning detection sensors. And the ground-based sensors look vastly different depending on who has manufactured it. There are just some long antennas that are used for time of arrival measurements. There are sensors that are actually two-looped metal rings, and those are your magnetic direction finding antennas. But they are located typically in an open area away from a lot of magnetic or electric interference. They've been placed in strategic locations to maximize their field of view, but they're found in cities, in farmland, just kind of all over, so that you get a wide view of lightning in either the United States, Brazil, Europe, or globally.
Okay, next question. What is the CG/CC ratio in your EEL cases? Can you use this parameter as a differentiating parameter?
Yeah, that is a good question, discussing the Z ratio. The Z ratio is the in-cloud CG ratio. And in this study, I only looked at lightning as a whole. This summer, there will be an algorithm update to the GLD 360 lightning network that I used the data from, which will differentiate between in-cloud and cloud-to-ground lightning. So I could go back then after that data is reprocessed to look at the Z ratio. I know some studies have been done on tropical cyclones that are closer to land, looking at the cloud-to-ground ratio in tropical cyclones. So there is some work done on that, but I will go back into this as I'm able to get some reprocessed data differentiating between the in-cloud and cloud-to-ground lightning in the EEL signature.
And who picks where ground-based lightning sensors are placed?
The developers of the networks pick the locations. They work with the groups or the owner of the property where they want to place the sensor, but it's the developers of the networks that pick the locations based on their current network geometry and what they are trying to do with their network. If they want to detect more in-cloud lightning, more cloud-to-ground lightning, or what the purpose of their network is.
Is the EEL the same as a lightning hole as shown in McKinney et al. 2009, published in EJSSM?
I will have to look at that and get back to you because I'm not familiar with that publication. So I will definitely look into that, and I can provide a response to that question.
That question came off of Twitter, so you can definitely respond via Twitter.
All right, I will do that.
All right, next question. So CoreLogic's StrightNet reports provide lightning locations to the 5th decimal point, which implies an accuracy of about 6 feet. How can they do that, since it indicates an accuracy which is not realistic? That's a toughie. Not sure if you'll be able to answer that, but go for it.
Yeah. I've seen some CoreLogic's reports, and I don't really want to get into how they discuss the accuracy of their reports or things like that. But traditionally, when you see a lightning dot on a map, it is within what is known as an error ellipse. So the lightning networks plot the lightning based on what they say is their best location of that lightning. But there is an error ellipse, which suggests that it could be somewhere within that circle on the map surrounding the lightning strike, or the strike point of the lightning.
All right, next question. We have a couple more, and we have about 8 minutes left, so we'll try to plow through all of these. All right, next one. Have there been any studies of correlation between the EEL signature and mesoscale convective phenomena that occur in the Eyewall, such as downbursts, tornadoes, etc.?
There has not. The EEL signature really came to be in the last 2 years. So the paper that was published last year was the first paper that was actually published on enveloped eyewall lightning. So I'm always looking for new areas in EELs to look at. Anybody is, of course, welcome to take this EEL phenomenon and start taking it into applications. Last year, I really wanted to get the definition of it out there, but there could be applications to it. And by all means, let's really start looking into what eyewall lightning in a tropical cyclone may mean, especially as it's making landfall, since convective areas in tropical cyclones can have stronger winds, heavier rainfall, tornadoes. So yes, let's keep going after studies on enveloped eyewall lightning.
You may have already touched upon this, but have you noticed if the environmental conditions vary between the EEL and non-EEL cases? Have you noticed anything that stuck out to you at all?
I haven't really noticed much between the environmental conditions of the EEL and non-EEL, because I haven't yet looked at the non-EEL environmental parameters. So next week I'll be, of course, discussing the environmental parameters of Irma, Jose, and Maria, but that is a new area to look into, is what are the environmental conditions in the EEL and non-EEL cases.
Sounds like a very interesting research project for you or anyone out there listening. And last question that I have, what are some good links? Where can we go to tweet and Facebook pictures, videos, safety info on lightning?
Well, on Twitter, if you use the hashtag lightning safety, that usually gets to most of the people that are involved with lightning safety. The hashtag of lightning, of course, is always a good one as well. National Weather Service hosts lightningsafety.noaa.gov, and they're always looking for pictures and videos and things like that, and they have a lot of great information on the science of lightning, the victims of lightning events, things like that. There are a lot of people working on lightning research and lightning studies. So if you look at the International Lightning Detection Conference, you can find a lot of great resources on people to work with and people to share videos and pictures and lightning safety ideas with.
Okay, I think that is it for questions. Thank you again, Chris, for a great presentation about lightning detection, and different applications. Thank you also to social media committee member Hannah Strong for live tweeting during the presentation. You both did a fantastic job today. I know I learned a lot. Well, that is all we have for now. Please join us next month as we dive into a talk about a tactical tool developed by NWS Tampa for mariners going in and out of Tampa Bay. The webinar will be held on May 2nd at 12 p.m. Central Time with our speaker, Mark Austin, who is a lead forecaster in the Tampa Bay office. So thanks again, and we will see you next month. Take care, everyone.